Hi, I'm Anastasia Thomas.
And I'm Katie Goebel. We're both graduate students in ASU's Masters in Biomimicry program. Biomimicry is looking to nature for lessons on how to solve human problems.
We're also both engineers. So when Katie told me she's interested in 3D printing, we both immediately asked, how does nature 3D print?
This question reminded me of a quote I read in Janine Benyus's book, Biomimicry: Innovation Inspired by Nature. In Chapter 4, How Will We Make Things?, Janine talks about how organisms make hard materials layer by layer. Nature's inorganic materials are tough, used for skeletal structure or protective armor, the shells and bones and spines and teeth of the natural world. There are crystallized versions of earth-derived materials, chalk and phosphates, manganeses and silica, even some iron thrown in for bite. Since organisms don't produce these inorganic materials in their own bodies, they must find a way to tempt and tame the particles of the earth to settle and crystallize in just the right location.
And it reminded me of an episode on a podcast called Ologies that focused on biomineralogy with biogeochemist and biomineralization expert Rob Ulrich. We were also lucky enough to get support from Mark Dorfman and Michelle Feller, who are both biomimicry professionals with experience in chemistry and visual communications, respectively.
Our goal for this project is to develop the outline for the printing process and uncover as many biomineralization models as possible. So, we started by investigating current 3D printing practices.
Traditional 3D printing typically involves polymers that are melted or cured together to form layers. It's a process that can require a lot of energy. Another downside is the release of gaseous compounds as the polymers are heated. Many of these compounds can cause damage as they are absorbed into the lungs and bloodstream.
Additionally, many polymers used for 3D printing are petroleum-based, so all the hazards that petrochemicals create, such as oil spills, cancer-causing byproducts, and microplastics, are inherent to these materials.
Clearly, 3D printing has a lot of potential, but also has a high environmental impact. Incorporating biomimetic principles means using low energy processes, a small subset of elements, and creating biodegradable materials, all while providing a robust, resilient end product.
To inform the design of our 3D printer, we looked at the functions biomineralization performs. Our primary function was, how does nature chemically assemble minerals and mineral polymer composites into physical structures?
So then we went on an exploration of biomineralization, and we found it everywhere, from the bottom of the ocean to mountain tops and everywhere in between.
One great example of biomineralization is a mollusk. These are water-dwelling animals that form shells around their soft bodies for protection. To form the inner portion of their protective shell, which is called nacre, mollusks use a mineral called aragonite, in addition to amorphous calcium carbonate and chitin. Their inner nacre is like a brick-and-mortar wall. They create a scaffolding made of the polymer chitin and coat it with proteins that bind to ions and cause crystal formation. This coated scaffold attracts calcium out of the surrounding water, which attracts carbonates to create pockets of amorphous calcium carbonate. The scaffold proteins and magnesium in the water cause the amorphous material to crystallize into aragonite. Each aragonite crystal is a hexagonal disc that's coated in amorphous material and is embedded within the scaffold like a brick in a flexible wall, so it can hold up to forces without cracking.
And biomineralization isn't exclusive to the animal kingdom. This tough strategy has been found in every kingdom, including plants. Sorghum, also called great millet, is a species of grass that produces a tasty grain. Possibly related to herbivory deterrents, sorghum has developed specialized cells which gradually form and are filled with silica. The sorghum plant's roots take in silica precursors from the soil, then form a supersaturated salicylic acid. This acid is then pumped through the transpiration stream into fluid filled cell walls of specialized cells called silica cells. When these cells are ready for silicification, the cell walls start creating a specialized protein that precipitates silica from salicylic acid. The silica crystals then nucleate within the cell walls of the silica cell until the cell wall is completely replaced by silica. These newly hardened cells offer additional structure support to the sorghum's leaves and also make chewing them a generally unpleasant experience.
In addition to this, we found some more examples of biomineralization that were interesting, such as gar scales, stony coral skeletons, armadillo shells, and parrotfish teeth.
And some of my favorite examples are the stinging nettle hairs, sea urchin spines, and bloodworm jaws.
Bloodworm jaws?
Yeah, they reinforce their jaws with copper to strengthen their bite and potentially to store copper, which they also use as a catalyst for their toxin.
Wait, toxin? Wow, so multifunctional. This is also a great way to describe the 3D printing process these amazing models helped us develop. The key steps for the process we developed are 1. Create a polymer scaffolding for mineral attachment. 2. Transport the input mineral material to the polymer scaffold site. 3. Create conditions for nucleation and crystallization. 4. Repeat the previous steps as needed for additional layers or structures. 5. Detach material to move to its functional location.
The benefits of this biomimetic model for 3D printing are many. High temperatures would not be needed, thus, the associated high energy consumption and carbon emissions would be avoided. Additionally, the process would use similar materials as biogenic minerals, so it would only use a small subset of elements. Finally, it would not give off toxic gases, but would produce completely biodegradable end products.
Biomineralization is a complex process, with mineral formation making up a small piece of the puzzle toward creating a bioprinter. For future work, we have identified a number of steps.
First, additional research is needed to better understand the full process, with areas including material transport, interfacing materials, structure, nucleation, wear, secondary functions, specific organisms, operating conditions, and applications.
We need to develop a proof of concept that demonstrates biomineralization ideas, applied to new printing processes, and then perform iterative prototype development.
In closing, we'd like to thank nature for sharing these incredible lessons with us and express our gratitude to research scientists for helping us understand these lessons, including our support committee members. We thank our classmates for their support and peer feedback along the way, and our partners for their patient support.
We would love to collaborate with any interested parties on future project development. More detailed information on this project can be found in our final report, listed in the comments, where you can also find our contact information. Thanks for watching.